towards full Galilei general relativity, Bargmann, Minkowski, and Bargmann-Galilei spacetimes. So after an introduction, I will recall Minkowski spacetime M and Galilei-Newton spacetime G, the decomposition of these into time and space, a material particle on M and G, and then I will introduce extended Bargmann spacetimes BM and BG, and then conclude. In terms of space, so-called non-relativistic physics is, in an important sense, just as relativistic as so-called relativistic physics. Space is mixed into time in Lorentz, that is, homogeneous Poincaré transformations, but not in homogeneous Galilei transformations. However, time is mixed into space in both Lorentz transformations and homogeneous Galilei transformations. Thus, the presence of relativity in both cases, albeit space only in one case, and both space and time in the other, justifies more careful reference to Galilei relativity and Poincaré relativity instead of non-relativistic physics and relativistic physics. Having freed the term relativity from specific attachment to the world according to Einstein, and recognizing its relevance to the world according to Newton and Galilei, the terms special relativity and general relativity should be reconsidered as well. The distinction between flat and curved space-time is what ought to be meant by the terms special relativity and general relativity, without regard for whether the physics is governed by the Poincaré group or the Galilei group. What distinguishes special relativity from general relativity is whether the group in question applies to space-time globally, in which case it is flat, an affine space, or only locally, in which case its curvature is determined by its energy, momentum, mass content. The proper references then would be to Poincaré special relativity and Poincaré general relativity, and to Galilei special relativity and Galilei general relativity. One might hypothesize that these linguistic shifts, unavoidably associated also with conceptual shifts, point toward a unified perspective on Poincaré and Galilei physics that may bear fruit in a strong field, Galilei general relativity, more extensive than the weak field, Newton gravity, presently known. As a first step toward this goal, a 5D Bargmann extension of four-dimensional Minkowski spacetime that limits nicely to the five-dimensional Bargmann extension of 4D Galilei-Newton spacetime is described here, and the metric tensors of possible corresponding 5D curved spacetime generalizations are displayed. Minkowski spacetime M is flat, a four-dimensional affine space. The invariant structure that governs causality is the null cone. The null cone. Here, this invariant structure, we have space here and time here. The null cone is embodied in a four-metric G. With respect to a Minkowski basis, the metric G is represented by this matrix. Note the speed of light here in the time-time component. This Minkowski matrix is invariant under a Lorentz transformation represented by Pm. An element Pm plus of the restricted Lorentz group can be factored into a boost and a rotation. The inverse metric, G double arrow, is represented by this matrix. Note now we have 1 over c squared in the time-time component. And this is also invariant under Lorentz transformations. Given a metric G, we have metric duality between vectors and linear forms. That is to say, the raising and lowering of tensor indices. Okay, what do we have in the Galilei world in terms of space-time? Galilei-Newton space-time G is a degeneration of Minkowski space-time M as the speed of light goes to infinity. So the light cone here, this is in units where c equals 1. As c gets large and even infinite, that light cone opens up until it coincides with the spatial plane. The metric G asymptotes without a true limit in a manner that suggests a linear form tau equals dt becomes the invariant structure governing causality, embodying absolute time. So this is what we saw in the last talk with generalizations also. With respect to a Galilei basis, this time form is represented by this rho vector. The inverse metric on Minkowski spacetime limits sensibly to another invariant structure, the twice contravariant tensor gamma double arrow. And it's represented by this matrix now that 1 over c squared has become a 0 in this time-time component. The linear form tau is invariant under Galilei transformations, and similarly this degenerate inverse metric gamma. And these Galilei transformations are the c goes to infinity limit of the Lorentz transformations. And once again, there is a factorization into a rotation and a boost of these Galilei transformations. Now this tensor gamma double arrow, derived from G double arrow, does not qualify as an inverse metric tensor in the full sense because it is degenerate. It has no inverse. So there is no space-time metric on Galilei-Newton space-time G, and so your tensor algebra is more constrained. There's no metric duality, raising and lowering of indices. Changing of tensor types is not allowed. Decomposition of M and G into time and space. So affine spacetimes, flat spacetimes, permit inertial observers with straight world lines and no rotation. The splitting of space and time as perceived by a single inertial observer is formally similar on M and G. You select a Minkowski basis for M or a Galilei basis for G, designated like this. Then the tangent vector to the world line of a reference inertial observer is the constant for velocity n, which is the first basis vector. Then consider ST, spanned by E1, E2, E3, whose points have a time coordinate t. It is a hyperplane, a three-dimensional affine subspace of M or G. So interpret S of t as space, according to the fiducial observer at her time t, a surface of simultaneity. Now it's evident from this factorization P equals LR, the boost in rotation, that this space is rotationally invariant. Thus S of t is endowed with a Euclid metric gamma, defining the usual spatial or scalar product on R3. Each hypersurface ST is a level surface of the coordinate function t, and the complete collection of these space slices is said to be a foliation of M or G. The vertical lines in a spacetime diagram of M or G are the world lines of a set of inertial observers. The horizontal lines in a spacetime diagram represent position space at time t, the leaves of the foliation. So that's these vertical and horizontal lines in these images of Minkowski spacetime or Galilei-Newton spacetime. A material particle is represented by a time-like curve, x of tau in spacetime, parameterized by the particle's proper time tau. And the tangent vector to this time-like curve, the world line, can be decomposed into measurable pieces parallel to n and tangent to st. This follows from representing, according to this representation here in terms of 4 vectors. This leading factor, d tau dt, is determined by the fundamental structures, the metric on m, or the clock form or time form on g, which give these time intervals that relate the proper time d tau to the coordinate time dt, which is the proper time of the inertial observer. Okay, so far so good on both m and g. A space-time description of particle kinematics, that is to say, specifying where a particle is and how fast it is moving. This is unproblematic in both m and g. However, a space-time formulation of particle dynamics turns out to be more problematic in the Galilei case. Because of the absence of a space-time metric, there is no equivalence between inertia and total energy. No E equals lambda mc squared, where lambda is the Lorentz factor. So Lorentz or homogeneous Galilei transformations transform inertia, but do not demonstrate the transformation rule of kinetic energy, which is strictly separated from inertia on G. So this motivates the extensions of the Lorentz and homogeneous Galilei groups that address the transformation of kinetic energy in order to obtain a more unified perspective. This is necessary for Galilei physics. It's not necessarily for Poincaré physics, but it is allowed, it's possible, and allows you to obtain a more unified perspective. So we look toward an extended Bargmann-Minkowski or Bargmann-Galilei spacetime by considering a 5-velocity u hat that extends the 4-velocity u on m or g. And the 5th component will be the kinetic energy per unit mass. Galilei version and Poincaré version. Adding an additional dimension means you add an additional coordinate, and so a point is represented by these 5 columns where we have an extra coordinate eta now. The proper time tau is governed by g or tau as before. These are now regarded as tensors on Bm or Bg respectively. And this 5th component of this extended spacetime must satisfy these relations from the previous, which come from the previous slide. d eta d tau is equal to these expressions. So it's apparent that eta has units of action over mass. Call it the action coordinate. And this action coordinate relation here, whether in the Poincaré case or the Galilei case, will prove crucial to the geometry of these extended spacetimes Bm and Bg. So we want next to determine the 5x5 Bargmann-Lorentz transformation matrices and Bargmann-Galilei transformation matrices that appear in the transformation rule for this 5-velocity. In 4+1 block form, it looks like this. This is the usual Lorentz or Galilei transformation, and then we have this additional structure here. So this form ensures that the time-like 4-velocity character of u on m is preserved in the 5-dimensional setting when it's extended to u hat. The 4 row here, phi, in this transformation is determined by the transformation rule for kinetic energy. So these sets of B Lorentz transformations or B Galilei transformations are subgroups of GL5 and indeed subgroups of SO14. They preserve a Bargmann metric or B metric capital G, whose form with respect to a B Minkowski or B Galilei basis is suggested by that action coordinate relation, that key equation I highlighted earlier. This is the form of these metric. So instead of a c squared in the time-time component, you have a 1 over c squared in the eta-eta component in Minkowski physics. It's a translation of Minkowski physics into the 5-dimensional setting, if you like. And now instead of having trouble when c goes to infinity, when c goes to infinity, you here get something nice in the Galilei case. So now, and the inverse, similarly, you have 1 over c squared here as before, and that also gives you a nice limit. So note the remarkable difference in the relationship between m and g on the one hand, the 4-dimensional setting, and between bm and bg, the 5-dimensional setting, on the other, including startlingly different geometric consequences. So in 4 dimensions, spacetime M is a pseudo-Riemann manifold with metric G and an inverse. And Galilei-Newton spacetime, which you get as c goes to infinity, is not a pseudo-Riemann manifold. Instead of a metric and its inverse, one is left with a time form tau and an invariant degenerate inverse metric gamma double arrow. In contrast, in the 5-dimensional setting, both Bm and Bg are pseudo-Riemann manifolds with a metric capital G and inverse. And the versions of both of these, metric and its inverse, on Bm limit smoothly to those on Bg as c goes to infinity, as we saw in the previous expressions. Okay, so looking forward, the next step is to relax the assumption of a flat affine space, allowing instead space-time curvature determined by energy momentum content. In terms of a lapse function alpha, a shift 3-vector beta, and a 3-metric gamma of the standard 1 plus 3 Einstein spacetime, traditionally we call general relativity. So the usual 1 plus 3 splitting of general relativity with these functions. In the 5-dimensional setting, as the action coordinate relation from before suggests that this is the translation of usual Einstein relativity into the 5-dimensional setting. Lapse function, shift vector gamma here, but now 1 over c squared instead of a c squared in the time-time component. And its inverse. And as c goes to infinity now, we get a smooth limit to something where now we also have a lapse function and a shift vector and a 3-metric. But now this would be Galilei physics version. So this suggests that there is a reasonable prospect that recasting the 1 plus 3 formulation of the Einstein equations in 4 dimensions as a 1 plus 3 plus 1 formulation on this extended space-time, BE, and taking the c goes to infinity limit could yield a strong field Galilei gravitation on a space-time B script G. So the interesting possibility might be that energy density and stress may contribute as sources and give rise to space as well as space-time curvature beyond the flat space slices and space-time curvature determined by mass density alone in Cartan's weak field reformulation of Newtonian gravitation. This would be a useful and conceptually and mathematically sound approximation in astrophysical scenarios such as core collapse supernovae, which is the field I work in as an astrophysicist, in which the energy density and pressure of the nascent neutron star contribute to enhanced gravity at the 10 to 20% level, but for which the computationally and numerically fraught phenomena of Minkowski bulk fluid flow and back reaction of gravitational radiation are much less significant. So this is a picture in Newton-Cartan gravity. You have flat space slices, And the curvature here is all in the space-time curvature. And this eta here is in this third dimension. So you have this, instead of a 1 plus 3 space-time, you have 1 plus 3 plus 1. So the suggested possibility here is that you could have something more general where you have absolute space slices here, but they are curved instead of flat, as in the weak field gravity case. This is a postulated or suggested possible strong field Galilei gravitation. So here, this is the archive handle for my proceedings here in this meeting, and then I have a longer paper, the first part of this study here recently available as well. So this is kind of a logical roadmap to the spacetimes I have mentioned here. We have on one side the 4D traditional spacetimes and then 5D Bargmann extensions. This is flat Minkowski spacetime, traditionally called special relativity. Einstein generalizes that, traditionally called general relativity. With hindsight, then, you have four-dimensional spacetime Newton physics or Galilei physics. Here, this is the curved Newton-Cartan, and then it's flat affine space versions. So Bargmann spacetime, which originally came about from considerations of quantum mechanics, is a central extension, as was also mentioned in the previous talk, of the Galilei group. And you can consider also the Newton-Cartan version of that. So my suggestion here is something different from Newton-Cartan. Today I have mentioned a five-dimensional Bargmann-Minkowski, which corresponds to the Bargmann group in Galilei physics as normally traditionally thought of. My suggestion is that to try to formulate from standard general relativity, according to Einstein, an extended version, which then will lead us to this strong field Galilei general relativity that is my goal. Thank you.
Thank you very much. Now the questions. Yes, it's very, very interesting relaunch of Bargmann's setting. What about the electromagnetic fields? Which is your opinion on this issue?
So yes, electromagnetic fields are discussed in this preprint here, that recently available in the archive. And electromagnetic fields are interesting to consider because that's what gave rise to Poincaré physics in the first place, the Poincaré group. And it turns out that that fits into the five-dimensional setting without any new physics required. It fits in nicely in a way that I show in this paper. If you take the Galilei limit, there's two possible Galilei limits of electromagnetism, so-called electric and Galilei limits, and that story was first worked out by Le Belloc and Lévy-Leblond in 1973. And so here I discuss those two limits from a space-time perspective, which they did not use, and I think the story works out in a very nice way from the space-time perspective. So in the case of electromagnetism, no new physics when going to the, in flat space-time at least, when going to the five-dimensional setting. But I still think there may be something new in terms of gravitation in the five-dimensional setting.
Maybe I missed this, but why do you want to have C to infinity? Why do you want to get rid of the cones when I can interpret it like that. What is, so maybe in other words, what's the problem with the 4D formulation? Why is a 5D formulation of special and general relativity more beneficial? So I didn't really get this. Sorry.
Please.
Oh, sorry.
Microphone.
Thank you. So in my day-to-day work as an astrophysicist studying core collapse supernovae, it would be useful to have an approximation where you have stronger than Newton gravity, but where you don't allow relativistic macroscopic bulk velocities. And so that kind of theory is what I'm trying to get to, a stronger Galilei relativity where I don't allow, I don't worry about Lorentz factors and so on of the bulk fluid flow, but I do want the stronger gravity from internal energy density and pressure contributing as sources of gravity. So that's the kind of approximate gravity I'm after. A strong field Galilei gravity is one way to think about it.
Another question? In the original works of Bargmann, it was, as you said, applied to quantum mechanics. Are there some applications of what you are doing to quantum mechanics? Of course, you are interested by cosmology, but is there something to do in the direction of quantum mechanics?
I don't know. The reason the Bargmann group is necessary for quantum mechanics here is even to show that the non-relativistic Schrödinger equation is Galilei covariant. It has to do with you don't have a unitary transformation. You only have unitary representation. You only have projective representations under the Galilei group, and so you need this extra dimension to show you get these extra phases and things, and that's not necessary in the Poincaré group.
Extra dimension is compactified.
I don't know, I'm not sure. But yeah, when you're thinking about the quantum case and the Lie algebra of these groups, then the topic of cohomology comes up, and the cohomology is different. It's simpler in the Poincaré case. You don't have to worry about it. So I don't know if there's anything new or different in terms of that story, or in quantum mechanics. I don't know if there's anything new or useful there.
Thank you. The last question.
No, it's just a quick comment. Is that so? If you take the limit of a particle, it's really a choice. Either you do what you said. You take, let's say, you go to the Schrödinger equation. Because then, if you take the limit, you really do a redefinition with an U1 factor, and that leads then to this extra projective representation. But for instance, if you take the limit of a Galilean particle, as I discussed in my talk, you don't do that, and then you don't get. But of course, then you don't get the Schrödinger equation. Then you get an exotic particle, but that's a different limit, which then does not lead to the Bargmann algebra. So there are two ways of taking the limit. One in which it's your choice you make.
The two ways is the other side, the Carroll that you mentioned. Is that the two limits you're talking about? No, something different.
I need to. So, for instance, if you want to get a Schrödinger, you always have to start from a complex scale because it's complex, the Schrödinger equation. And then, if you take the limit, you do a trick. You redefine your field with a phase factor. That leads to Bargmann then. But if you take a real scalar field, you can't do that. But then you can take the Galilei limit, but then of course you get an exotic Galilei particle, something else. So it's a different limit. So there are also limits which do not bring to Bargmann, but then it's a different limit. There are different ways of taking limits, let's say. That's independent of Carroll. For Carroll you can do a similar thing, but in other words, the world of course contains physical electrons, etc., the ones you want to study in the stars, but if you take a different limit you also get exotic particles. So you're not forced to get to the Schrödinger equation. That's what I want to say.
Okay. Thank you.